So today is one of the OTFS SIG online seminar series, and we are very glad that we can have Professor Robert Calderbank from Duke University to be here today to share our their recent research results on OTFS. And this is one of the OTFS SIG seminars, and if you are interested in joining us and get to know this technology more, you can follow these details. So today's talk is going to be Zak-OTFS for the integration of sensing and communication, and is given by Professor Robert Calderbank. And I guess everyone is very familiar with Robert, and he is a Life Fellow of IEEE, and he directs the Rhodes Information Initiative at Duke University, where he is a distinguished professor of electronical and computer engineering, computer science, and mathematics. He studied his career in Mathematical Sciences Research Center at the Bell Labs, and he left AT&T in 2003 as Vice President for Research. Dr. Calderbank directed the program in Applied and Computational Mathematics at Princeton University before joining Duke University in 2010. He was elected to the National Academy of Engineering in 2005 and to the American Academy of Arts and Science in 2022. Dr. Calderbank received the 2015 Hemming Medal and the 2015 Shannon Awards. Very, very impressive. Dr. Calderbank is known for contributions to voice-band modem technology at the dawn of the internet and for contributions to wireless communication that are incorporated in billions of cell phones. He was also made contributions to the quantum error correction that provides a foundation for fault-tolerant quantum computation. Okay, without further ado, please join me to welcome Professor Calderbank for today's talk. Okay, I'll stop sharing.
Okay, I will start sharing.
Thank you.
Here we are. Now I just have to. There we go. Okay, well, thank you very much for a very kind introduction. So I'm going to be talking today about integrating sensing and communication. And I'll just say at the beginning that I think it's fair to say that the standard practice is to integrate by dividing resources between the two functions. And our perspective today is going to be different. We want to describe how sensing and communication can coexist in the same OTFS subframe. Now, I have to say at the beginning that this is not a math talk. And you might say, well, where did he hide the mathematics? Well, the mathematics is hidden in this this paper with my co-authors that's posted to arXiv. It's a long paper. It's 30 pages, double column. So there's plenty of mathematics in it. What I'll try and do today is to tell the story in pictures. And so here, every 10 years or so, we have a new wireless generation. And there's this lovely quote by George Orwell that says, every generation imagines itself to be more intelligent than the one that went before it, and wiser than the one that comes after it. What I've done here is I've made a slide talking to the progression of standards. I'm old enough to remember 2G. So when I worked for AT&T, we were thinking about the migration from IS-136 to CDMA in the 1990s. We had the transition from CDMA to OFDM. So there, that was driven by high-speed data. And technically, there was an opportunity to think about the benefits of adaptation. And every time we make a switch, we make a calculation that the benefits of switching outweigh the benefits of not switching. And I think what Orwell is reminding us is that there are actually things that we liked about the previous generations. And one of the things that will come out of today's talk is, there were things that we liked about CDMA, right? We liked the fact that it was a noise-like waveform. We thought that that made it more secure. What we didn't like about CDMA was that there was no relationship between the channel and the spreading sequences. And so equalization was not really possible. And so one of the things that we'll describe today is it's almost like a CDMA that you can equalize. All right. Now then, let's think a little bit about 6G. And I picked out two of the central challenges. One is AI and communications, and the other is integrated sensing and communication, which is the theme of today's talk. Ronnie's talk last time, I think of this as really being about AI and communication. So machine learning revolutionizes the world. All our students know it's the most important thing that ever happened in the history of the world. Now, you can continue to use OFDM signals, and when they get into trouble, you can have a big complicated neural network help them out. So it's clear that machine learning can help traditional methods of wireless communication. What we want to do is to ask a more fundamental question. We know we're going to have machine learning applications. We want to ask, what physical layer do they want to see? And what I would suggest is that the characteristic of the physical layer they want to see is predictability. And if you were here last time for Ronnie's talk, he's really talking about how you engineer predictability. All right. And so here, second thing is integrated sensing and communication. And so here the problem is that the signals you use to transmit data, they interfere with the signals that are used to sense the propagation environment. How can both coexist in the same subframe without compromising the effective throughput? So here's the plan. So the first part of the talk is it's actually going to go over the ground that was covered by Ronnie in his talk. So here we're going to separate sensing and communication. So we're going to have one Zak-OTFS subframe where we sense, and then a second OTFS subframe where we communicate data. And that's going to provide the baseline for integrated sensing and communication. Next up, we're going to describe how you integrate sensing and communication with what I'll call point pulsons. And this is really about dividing resources in the delay Doppler domain. And then we're going to talk about filters. So this is a new idea which enables coexistence in the same subframe and no division of resources. And we'll try and give you some numerical simulations that give you some insight into the process. So for this first part on where sensing and communication are separate, the background is found in these two magazine articles. We hope they're easy to read. They took us a long time to write, so we're quite proud of them. All right, so here we are. Separate communication and sensing. So we send a pilot, that's XS, and we read off the I/O relation, the input-output relation, from the response to a single pilot signal. This is something Ronnie described last time. I'll describe it a little bit this time. In the magazine article, we just read off the I/O relation. And that works pretty well, but it's not maximum likelihood. The maximum likelihood algorithm is to calculate the cross-ambiguity of what you received and what you sent. And that's described in our paper. It's also described in a really nice paper by Stephen Hanley's group from Macquarie in Australia. So we read off the I/O relation, and then we use the channel estimate to equalize, to recover the data in a subsequent frame. And one of my goals here is to convince you that you actually already knew this stuff. Because as electrical engineers, you're really familiar with LTI channels. And the only difference between LTI channels and LTV channels is that one's one-dimensional, one's two-dimensional. But if you think about an LTI channel, time domain pulse, that's a geometric mode. What do I mean by that? What I mean is that the I/O relation is just made up of delays that move the pulse in time. That's what it means to be a geometric mode. And if you wait longer than the delay spread, then you can read off the I/O relation and equalize the data. And predictability just means that the I/O relation doesn't change with time. And so when we talk about crystallization, when we talk about predictability, you've actually already seen this on LTI channels, where the relationship between input and output is given by convolution. Now, we, of course, are going to two dimensions, and we're going to a pulse, not in the time domain, but in the delay Doppler domain. And as Ronnie said last time, you have to be careful, because you can't have a pulse in the delay Doppler domain, because then it would be improperly localized. It would violate Heisenberg uncertainty. And the way that you get around that is by introducing a quasi-periodic function. And so if you look at this picture, there's a delay period tau p and a Doppler period nu p. So there's a fundamental period, and we put a pulse in the middle of that fundamental period. And then as we move integer multiples of tau p along the delay axis, we introduce a phase. As we introduce integer multiples of nu p, we don't do anything. So that's how you should think of a quasi-periodic function in delay Doppler. And what we're going to do is we're going to say, how do we choose the size of this box? We say, you're a wireless engineer. You know what your delay spread is. You know what your Doppler spread is. We're going to choose the size of the box to capture the delay and Doppler spread. Oops. All right. Now, of course, we don't transmit things in the delay Doppler domain. We have to get to the time domain. How do we get to the time domain? We apply a transform. It's the inverse Zak transform. And the pulse becomes a pulse train, and the duration is t, and the bandwidth is b. And t and b are related to the dimensions of the pulse. So 1 over b is the width of the pulse in delay, and 1 over t is the width of the pulse in Doppler. Okay? The position of the pulse The delay tau 0 tells you about the offset of the pulse train, and the Doppler coordinate nu0 tells you about the modulating tone. A point that I'd like to make is that you achieve the time bandwidth product, and I think this is actually a nicer picture of functions that are essentially limited to a certain bandwidth and a certain time. So these pulsones, which is what we call them, they're a mixture of a pulse train and a tone. If you shift them 1 over b, they don't see each other, so they're orthogonal. And if you change the modulating tone, then they're also orthogonal. So it's like you've got an orthonormal basis for functions that are time and bandwidth limited. Now, what we've just described here is really a family of functions which are indexed by tau p, because we're always going to choose the product of tau p and nu p to be 1. So we're looking at underspread channels. And so this family of waveforms lives on a hyperbola. And at one end, you have single carrier. And at the other end, you have multi-carrier. I mean, let's think about single carrier. As you grow the delay period, the time domain pulses get further and further apart, the tone structure disappears, and you're just left with a single pulse at tau 0. Let's think about multi-carrier, or FDM. As you shrink the delay period, the pulses grow closer together, the pulse structure disappears, you're just left with the tone. So there we are. Now, we're going to talk now a little bit about predictability. And so here the idea is you send a pilot, or you send one of these delay Doppler pulses, and you look at what you see as a response after the channel. Well, you see the channel shifts the pulse you sent in delay and Doppler. And the point of this slide is that if you sent a pulse at a different point, you get the same pattern of replicas. So if you know what happens at one point in the fundamental domain, you know what happens at every point. How do you get from the inputs to the outputs? Well, it's something called twisted convolution, which is just convolution with a twist because it involves phases. And so there's a function h of delay in Doppler, which gets twisted convolved with the input. And what I want you to come away with is the idea that twisted convolution is just like convolution. The other important thing about twisted convolution is that when you apply a filter, or whether you apply a channel, you get a cascade of twisted convolutions. And twisted convolution is associative. So all of these things smush together to produce an effective channel, which you can then acquire. This is the picture from the magazine of the signal processing transceiver chain. And here at the bottom, there's this point about associativity of twisted convolution. You see the transmit filter and the channel and the receive filter. They all get smushed together to make an effective channel HDD. And that's what we acquire, and that's what we use to equalize the data. All right. When Ronnie gave his talk, he talked about the crystalline regime, or the crystallization conditions. The crystallization conditions are really simple. One way to express them, it's not the most general way, we'll come to the most general way in a minute. We want the delay domain period to be bigger than the delay spread. And we want the Doppler domain period to be bigger than the Doppler spread. And if those two conditions are satisfied, then the interaction of a doubly spread channel with a time domain pulsone is predictable and geometric. We're going to explore predictability by thinking about unpredictability. So this is a version of a slide that Ronnie gave last time. And so the idea here is that you're electrical engineers. You know everything about aliasing. Perhaps you don't know about aliasing in the delay Doppler domain, but it's aliasing in the delay Doppler domain that controls predictability. So what Ronnie described last time is if you're in that, let's look at the bottom right, and suppose that you're in the dark purple area. Well, when we made this quasi-periodic function, we had replicas. And if you're in the dark purple area, you feel two replicas. And so what happens to you is a linear combination, if you like, of two variables. If you were at a different point in delay, you would feel two replicas, but you'd feel them in a different way. You would be a different linear combination of two variables. And you can't predict one from the other. And that's the mathematical reason for time selectivity. So aliasing in Doppler gives you time selectivity. Aliasing in delay gives you frequency selectivity. And if you arrange things so that there's no aliasing, you get predictability. And that's the crystalline domain. That's the place where the crystallization conditions hold. So there's this hyperbola that takes you from single carrier to multi-carrier. And if you operate at a good spot in the middle, you're a little two-dimensional Gaussian channel. You are perfectly predictable. So the point in this slide is fading is an act of self-harm. It's something that you do to yourself by not configuring the fundamental period properly. Now, I should say something about I gave you this recipe for the crystallization conditions. And I'll make it a little bit more general later, but this is the picture from Ronnie's. And throughout this talk, when we show numerical simulations, what we do is we pick a model. We actually pick the vehicular A model. So it has 6 paths. And the reason that we pick the model is that it's representative of real propagation environments. And we also pick it because we're not going to give the simulation enough time and bandwidth to be able to separate the paths. So the paths can't be separated with the bandwidth and time that are available. The take-home message of this slide is, so in this slide, what we do is, so the blue star curve at the bottom, that's perfect channel estimation. So a Gini tells you the channel. The interesting thing is the square curve that's just above, because there what we do is we send a pilot, we acquire the input-output relation, we just read it off. And then we use that input-output relation to recover the data, to equalize the data. And we refer to that mode of operation as model-free. So a point of this slide is stop estimating channels. Channels aren't important. What's important is the interaction of the channel and the modulation that you've chosen. You want that interaction to be predictable. You don't care about the channel. Okay? So I'm exaggerating a little bit to make a point. Okay. Now we're going to start. That's my review of Ronnie's talk from last time. And so that's separate sensing and communication. So 1 millisecond OTFS subframe for sensing and a second one for communication. Now then, we're going to integrate sensing and communication, and we're going to use point pulsons. So that means that we're going to use a single pulse in the delay Doppler domain. So a single carrier. Now, what's the conventional wisdom on integrated sensing and communication? And so here, I've stolen this slide from a talk that Vince Poor gave recently. He says, joint sensing and communication. He says, fundamental trade-offs. For the purpose of sensing, the waveform should be sensitive to the environment. Agree completely. Second point, for the purpose of communication, the waveform should be insensitive to the environment. What I hope to convince you of in the rest of the talk is that the second point is simply wrong. I know what Vince means. What should be insensitive to the environment is the input-output relation. But that's an important difference. All right. So what are we going to do? So here we're going to operate in the crystalline regime. We're going to send a point pilot, and we're going to send data. And I'm going to argue that we're going to need a guard band to separate the pilot from the data. So this is what I mean by dividing resources between sensing and communication. So we transmit a superposition of the pilot and the data, and we receive some signal YDD. And here we receive it in the delay Doppler domain. And so we transmit XP and XD, and we receive YP and YD. And what we're going to do is we're going to estimate the effective channel. Once we've done that, we can figure out what the contribution to the received signal YDD was from the pilot. And we could subtract that estimate. So we just have a data signal, Y hat D. And then we use that signal and the estimate of the channel that we have to detect the data. All right, let me convince you that you need guard bands. Well, the If you don't have a guard band, what happens is that interference from the data completely obscures the effective channel taps, and so you're not able to sense. And so this is a picture of what you, if you didn't have a guard band, this is what you would observe in the delayed Doppler domain, and can't do very much with it. If you have a guard band, then the effect of the guard band is to create a little window around the pilot where there's little interference from the data and where you can acquire the effective channel. So I would argue here that if you're going to use point pulsons for pilots and for transmitting data, then you're going to need a guard band. Here in the paper, there's all of the details about the numerology and stuff, and I won't talk about them here. Now, throughout the talk, we're going to use this this abbreviation at the top here. So what do I mean? So S is sensing and C is communication. And when I do S given C, what that means is sensing in the presence of data. When I do C given S, that means communication in the presence of a pilot. When I say S given C bar, that means sensing no interference from data. C given S bar, that's data, no interference from the pilot. So that second thing, S given C bar and C given S bar, that's separate communication and sensing. So that's really that's the yellow curve in the picture. And that's the baseline for everything that we're going to be doing. Here, there are two yellow curves in the picture corresponding to different choices of filter. One is a root raised cosine filter, one is a sinc filter. Root raised cosine filters are better than sinc filters because they control better the leakage of energy outside of the guard band. See, when energy, we're going to acquire the effective channel in the region that we've carved out, there's going to be stuff that we don't get. And so that's what we think of as a residual pilot. And that's going to interfere with the data. And better filters means lower energy residual pilot, less interference, better performance. And you can see in the picture here that if the Doppler spread isn't too severe, then we can get somewhere like 10 to the minus 2, 10 to the minus 3. It starts to go a little, you can look at these curves and you can convince yourself that with coding you could make a system. We haven't done that in this presentation. All right. Now then, if you were a hardware engineer, you would look at these pulsone waveforms and you would say, ooh, that's a really nasty waveform. That is seriously unattractive. And the reason it's unattractive is that it has a bad peak to average power ratio, maybe like 15 dB. And So for comparison, if you took each of the MN carriers that you have and you modulated with random for QAM, took the superposition, the PAPR would be like 8 dB, something like that. So peak to average power ratio is a problem. And now we're going to solve that problem by thinking about filters in the discrete delay Doppler domain. So the picture that you should have in mind is that this hyperbola interpolates between single carrier and multi-carrier, between TDM and FDM. These filters allow you to push out into CDMA territory. So filters are going to be what allows you to make a noise-like waveform. Now, we draw inspiration from radar. So what do radar engineers do? Radar engineers construct waveform libraries for tracking targets by manipulating self-ambiguity functions. Okay, so here we've got so it's mathematically, we have a waveform phi, we have an operator d of tau nu, which shifts in time and shifts in frequency. How do you get an ambiguity function? You take the waveform, you shift it in delay and in Doppler, and you take the inner product with the original waveform, and that gives you a surface that lies above the delay Doppler plane. That's called the ambiguity surface. And a fundamental theorem in radar says that the volume of that surface, you can't do anything about that. It's basically the energy squared of the waveform phi. That's Moyal's identity. So you're a radar engineer. You can't do anything about the volume under the ambiguity surface. What you can do, though, is you can move it around. And what radar engineers do is they move it around so that at some point there'll be a waveform where the target is not obscured. So that's what you mean by a waveform library. You have a waveform phi, and then you're going to move it around, and you're going to illuminate your scene with all of the waveforms you have, and you hope that the target is going to be visible in one of them. How do radar engineers move waveforms around? One of the ways they use symplectic transforms. An example of a symplectic transform is chirping, so linear frequency modulation. And I've shown you what a chirp is with slope q. And what's true at the bottom is that what's the relationship between the ambiguity function of the chirped waveform and the original waveform? It's a rotation. And that's the content of the bottom line here. All right. And we are going to borrow from radar. So what we describe in the paper is how to make a discrete chirp filter. This is how we make a discrete chirp filter. So you can see k squared plus L squared, that's like t squared. And what we do is we make a spread pilot by applying this filter to a point pulse zone. Okay. Now, let me not do the theorem. Let me do. Show what I want. Actually, I wanted to say this. So, so that's how we make spread pilots. We actually have a lot of degrees of freedom in making a spread pilot, making one of these filters. The filter is actually periodic in both delay and Doppler with period mn. And so we have m squared, n squared degrees of freedom to choose. So we can actually do a lot with filters in the discrete delay Doppler domain. In the paper, there's quite an involved calculation, but the bottom line is this: we make a spread pilot in the way that I just described. The original pilot, its ambiguity function, it's just supported on the period lattice. I should say what the period lattice is. So there are three lattices that play an important role. There's the information lattice, which is this blue dots. That's where the data lives. These are the OTFS carriers. There's the period lattice. That's the green dots, right? That's where the ambiguity function of the point pilot lives, because you have these orthonormal functions. If you shift them in delay and Doppler, they're going to have inner product 0. So you're only going to be supported on the period lattice. And then you have this red dots. That's the dual of the information lattice. That's where the filters live. So data lives on the information lattice, ambiguity functions live on the period lattice, and filters live on the dual lattice. In the paper, there's this theorem that says you make a spread filter using this chirp in the discrete delay Doppler domain. The ambiguity function of the point pulsone was supported on the period lattice. The ambiguity function of the spread pulsone is rotated on a new lattice, lambda q, which is just obtained from rotating the old one. So it's just like radar. All right. Let me give you a picture of what this is doing. So on the top of this slide, there's the point pilot. So in the time domain, it's this nasty peaky waveform. After you've spread it, it becomes this really nice noise-like waveform. You can look at the y-axis. It's an order of magnitude difference here. If you want to look at the difference between a point pilot and a spread pilot in the delay Doppler domain, point pilots just focused at a single point. In the delay Doppler domain, the spread pilot is equally present in every one of the carriers. So if you have a unit energy spread pilot, it's got energy 1 over mn in each of the carriers. I mean, what I'm hoping that you get from this is that you look at these spread things and you look at the point things. They're sort of mutually unbiased. So if you're doing something with one in the presence of the other, you're just taking an SNR hit. So you can actually have coexistence. All right. So this is the summary of peak to average power. If you have a spread pulsone, 5 dB. If you have a point pulsone, it's 15. Data plus spread pulsone is about 8. Data plus point pulsone is about 12. All right, the geometry of sensing. So here so we've taken a chirp filter with Q equals 5 in this case, and the regular period lattice is just, you know, rectangular in delay and Doppler, and the blue dots mark the rotated lattice. And that's the support of the self-ambiguity function of the spread pulsone. The green rectangle with the black border, that's the support of the effective discrete delay Doppler domain channel. What does it mean to be in the crystalline regime? What does it mean for the crystallization conditions to hold? I told you that I would say something a little bit more mathematical. And what it is this. You take the support region for the channel, you translate it by the blue dots, and you don't want any of the translates to intersect. If that happens, the crystallization conditions are satisfied. You can recover the effective channel from the pilot. So it's possible to estimate the channel on the information grid from the response received from the pilot. So here, good geometry and bad geometry. So here I've got a spread pulsone. It's defined by a chirp filter with Q equals 3. I send XS, I receive YS, I use the cross ambiguity between YS and XS to visualize the effective channel. Good geometry means the crystallization condition is satisfied with respect to the rotated lattice. Translates of the support set do not overlap. So Q equals 3 is a very well-behaved chirp filter. Q equals 36 is much less well-behaved. It behaves well for 815 hertz of Doppler. If it's 12 kilohertz, the crystallization condition is not satisfied because the translates overlap. All right. Now, I'm watching the time here. So here, in the magazine articles, we only really talk about the green and the pink. So how we do transmit filters, receive filters. Oof. What we've just talked about is a new domain, the discrete delay Doppler domain, where we have these filters and where we can move towards CDMA and where we can dramatically reduce the peak to average power ratio. All right, let's do some curves. So here, there's a little bit of math has crept into this slide. So here, we're doing integrated sensing and communication with a spread pilot. So we have point data, we have a spread pilot, we have a channel. What do we get? We get a signal, which is a superposition of a data part, a pilot part, and a noise part. I'm going to forget about the noise. And so here, I'm looking at how did I get this YDD? I got it by twisted convolution of the channel with the data part and with the pilot part. I'm going to estimate the channel using the cross ambiguity of Y with the pilot. And so I'm really interested in that first term. And the second term is the interference that the data offers. And I'd like for that interference to be well behaved. And in fact, it is. That what this top line says is that the interference from the data is just has the same energy in each bin. So it just looks like an SNR hit. And so I can estimate the effective channel just by reading off the cross-ambiguity function. And then what do? I estimate the channel. I estimate the received pilot. I subtract the received pilot from the received signal. Then I recover the data. Oof. I notice that I'm getting a little short of time here. Here, I'm just keeping track of the sensing accuracy as a function of the ratio of the pilot energy to the data energy. The yellow curve is sensing with no interference from data, and the blue curve is sensing with interference from data. I'm increasing the ratio of pilot power to data power. In the end, I overwhelm the data and noise. I get a good estimate of the channel. So here, what's happening is I'm measuring. So I said before, we estimate the pilot, and we never get it perfect. There's always some residual interference. We estimate the channel within some support region. The taps outside, they're a bit noisy and subject to aliasing. So we don't get them perfect. Sensing accuracy improves as PDR increases, but so does the power of that pesky residual pilot. And so what happens, so in this curve here, the red curve is perfect CSI. The yellow curve is separate sensing and communication. The blue curve is integrated sensing and communication with a spread pilot. And you can see it has a U shape. Up to a certain SNR, we get a benefit from sensing the channel better. Above a certain point, where we're not doing anything good to the residual pilot, and the residual pilot interferes with the data recovery. So that's why there's a U shape. And so this is the bottom line. The yellow curve is separate sensing and communication. The blue line is integrated sensing and communication with a spread pilot, which is better than a point pilot, and it's okay. But you can see there's like 3 orders of magnitude. The other thing that's interesting about this curve is that you get small variation over a wide range of Doppler spreads. I want to choosing the right filter matters. This is a slide about effective throughput. So when you have a guard band, you're giving up degrees of freedom. So you're not going to be able to transmit as much information. When you're doing integrated sensing and communication with a spread pilot, you're not giving up anything. So you get a better throughput. And now we know in signal processing that turbo principle is magic, and it's magic here too. So what are we going to do? So in the first iteration, we estimate the channel, we estimate the received spread pilot, we recover the data after subtracting this estimate from the received signal. Now we can take the estimated data, estimate the received data signal, improve our estimate of the channel by subtracting our estimate from the received signal. So that's a turbo iteration. And 5 turbo iterations suffice to match the performance of separate sensing and communication across a wide range of Doppler shifts. So the turbo iterations close a 3 orders of magnitude difference in bit error rate, which is amazing. All right, conclusions. So, integrated sensing and communications reduces to geometric properties of a lattice used for data transmission. That's what Ronnie described in his talk. And a lattice used for sensing. This is the rotated lattice that I talked about. By sharing delay Doppler domain resources between sensing and communication, it's possible to optimize throughput without compromising bit error rate performance. When the channel satisfies the crystallization condition with respect to lambda q, that's the rotated lattice, you can read off the effective delayed domain filter taps from the response to a single spread pilot. When the channel satisfies the crystallization condition with respect to the period lattice, then given the input-output response at one point, you can predict the response at all other points. So that's high-level conclusion. Signal processing highlights. What we've figured out how to do is to use filters to create a different kind of signal, to control the interference between data and sensing. In a sense, well, not in a sense, we have produced 2 types of signal, and one looks like noise to the other. The fact that one looks like noise to the other means that both can coexist in the same space. We don't have to divide resources between the sensing function and the communication function. The other interesting thing about filters in the discrete delayed Doppler domain is that they can be used to design noise-like waveforms with excellent PAPR. Finally, just a note on passive radar. What is passive radar? Passive radar uses existing signals in the environment, often communication signals, as opportunistic illuminating sources. What's an example? DVB-T is Wi-Fi, and a long time ago, I had a student, Andrew Harms, who I sent to Australia to work with my colleagues in defense in Australia, who had used the DVB-T signal to image helicopters taking off at the local airfield. So what they did was they used the pilot in the DVB-T system as the illuminating source. What my student, Andrew Harms, did was design a mismatched receiver to use the pilot for this imaging purpose. The advantage of a passive system is you're invisible to countermeasures. The disadvantage is that the communication signals are not designed with radar in mind. Andrew actually had to do a lot of work to design his receiver. So what I've just described to you is how to make an ideal passive radar. Because the pilot in the passive radar should be one of our spread pulsons, and then there's the data. So there's, in the radar world, there's I think a real utility to this. All right, that is all that I have. I hope I didn't go too fast in the middle, but I'm happy to try and answer questions.
Mm-hmm.
And but that's the and yeah.
Thank you very much, Robert. That's a very great presentation. Personally, I learned a lot, and we also have a lot of questions. and I hope you
Okay.
have time to answer them. Um, I guess we can start from the meeting chat. So there were people asking the main bottleneck of OTFS, including, I think, Zak-OTFS, is the detection complexity and potentially the latency issue. Do you have any ideas how will this affect the practice?
All right. Let me be a little bit contentious since we're among
Of
friends.
course.
So let me contrast OFDM and OTFS, right? OFDM is configured to prevent intersymbol interference,
Right.
right? OTFS is configured to embrace intersymbol interference.
I see.
So you have to think about 6G systems and the balance between acquiring the input-output relation and equalization.
Right.
So in OFDM, acquiring the input-output relation in certain environments is really hard. Equalization is really easy.
Yes.
In OTFS, it's the opposite. Acquiring the input-output relation is really easy. And equalization of a two-dimensional Gaussian channel, well, you have to do some work, okay?
Right.
Now, what I would say is this. We've been in this situation before. In the 1990s, in data storage, in magnetic recording, we used to have peak detectors. A peak detector in magnetic recording is designed to eliminate intersymbol interference. At a certain point in the 1990s, we embraced intersymbol interference and we did partial response, maximum likelihood. What I can guarantee to everyone on the call is they don't have a peak detector in their laptop.
I see. Right.
So that's what I meant by being contentious. But that's in a sense what you have to think about.
Yes.
And
okay, I think that's a great answer. And we can move on to the next question. There were people asking for these figures you show that when you are comparing the bit error rate, for example, did you also include the potential SNR degradation due to the pilot power you transmitted?
absolutely. So in the paper, we spent a lot of time thinking about how you choose the ratio of pilot power to data power. So in the paper, we explore the data signal to noise ratio and the PDR, which is the pilot to, and we have a series of curves which we hope illuminate the issues that we're trying to balance.
I see.
Actually, I should also say that I think I have some of my co-authors on the call. So if there's a particularly difficult question, I will punt it to them. And they should feel that they can chime in too.
Yeah, for sure. Like, please. Okay. Also questions about this discrete delay Doppler domain filtering. Like when you are mentioning that you can use these to generate noise-like waveforms. There's one question I think is quite interesting that can we use this kind of filters to orthogonalize the data from different users?
Really good question. And we have some ideas on that question, but I think we're not quite ready to talk about them yet.
Right.
Okay.
So we are looking forward to your next publication on this topic then. Okay. There was also another question regarding the OTFS. Actually, I think it's more related to the channel models. So when we are talking about OTFS, it's obviously a wideband signal. And but the channel model is, people may argue, is actually narrow banded because we do not have this like a bandwidth scaling effect. Do you think how much this will influence our practice performance?
Okay. here I might try and punt to Saif if he's on the call.
Oh, is Saif here? Yeah.
Saif on the call?
Uh, I don't think he's here.
Oh no.
Oh,
Let me see who's so we
Ronnie is here.
okay, Ronnie, do you want to chime in?
Yeah, I'm.
And by the way, Ronnie, I hope you were okay with my summary of your talk.
Hi, Ronnie.
Again? Sorry?
Yeah, yeah.
Yeah, you're online.
I was out of my room. Somebody knocked on the door. There was a question addressed to me?
Yeah,
or
there
I
was a
just,
question. Yeah. So do you want to say the question again?
Yeah, of course. The question is about in practice, like when we are having this wideband signal, when we have like Doppler effect, the bandwidth actually become larger. So will this also affect the performance in practice using OTFS, of course?
So you're talking about sorry. So let's say you have the presence of Doppler.
Mm-hmm.
You have the presence of Doppler, and so you are asking whether the effect of the Doppler on the bandwidth of the transmission or
No,
on
it's
the size of the delayed Doppler response.
I think your received signal has a slightly larger bandwidth because of
But
this.
this is very small. The Doppler is
Right.
kilohertz. The bandwidth is megahertz. So,
Yes.
so this is a tiny effect. Okay, so you have this tiny Doppler extension, but I
I
don't
think
see how it can affect performance unless you are putting maybe the only situation, which is that this effect can have some influences when you're doing multi-user transmission and you're putting different users adjacent to one another in frequency, and then you're asking whether this Doppler effect can create inter-user interference. That's
Yeah,
one thing, because
so,
if it's a single user, who cares?
yeah,
But
and
if
I
you have
would say,
multi-user, yes.
yeah. So I was going to say, maybe the next talk will be Saif. We can, if he's not on, we can just volunteer him.
Right.
Because we have a new archive posting on Gaussian filters.
I see.
Yes.
And so that relates to what Ronnie was saying before. So we are really, so in the papers, you know, thus far, we looked at sinc and root raised cosine. But it's natural to look at Gaussian filters in the delayed Doppler domain.
Yes.
And Gaussian filters are wonderful because they fall off very fast. And the paper on archive wants to, you know, looks at, in the sense, the trade-off between time bandwidth expansion and predictability.
I see.
Right. So that's how I think about the archive posting.
And one small point regarding connecting what Rob said to what I said is that by using appropriate filters like Gaussians, you can introduce immunity to inter-user interference. So the filter can give you also this immunity to this inter-user interference that can be created, and you can pack the user close to one another in this way.
Yes.
Yeah.
Yes. I personally very agree with what you have mentioned. I think this bandwidth expansion may only be very significant for example, like underwater communication. So in general, it's not a big influence. And I think we have Abid here who wants to speak some questions. Yeah, please.
Thank you for giving me the chance to speak in this great session. Thank you, Professor Calderbank and Lee, for your organization and presentation such nice session. Actually, regarding the wideband issue of OTFS, I'm trying to convince you that unlike narrowband channels, in which the time contraction and time dilations are approximately modeled by frequency shift, in wideband channels, in addition to the frequency shift, we are dealing with time scaling of the signal. Namely, in other words, the more carrier frequency, the more frequency shift. So when we look at the structure of OFDM and OTFS in the frequency domain, the half power bandwidths of each subcarrier are all the same. But in wideband channels, for greater frequency, the shift of the carrier is larger. It seems that the half power bandwidths of subchannels should be different from each other.
Okay.
Might, of course, but please, Rob, answer.
No. Please, I was going to punt on this one, so I'm very glad if you pick it up.
You said, and if I need to add something, I will add.
No. You go ahead.
Okay, so you're right, Abed. Of course, thinking about the channel as collection of reflectors breaks down when you go to wideband and when the carrier frequency is small compared to the band. That's a precise condition. When the carrier frequency is small compared to the band.
Yeah, exactly. I agree with you that the fractional bandwidth is near to unity, but I'm talking about the scale.
It's
changes
true.
of the
but okay, so what you're saying is that this whole idea that the channel consists of reflectors which introduce a constant Doppler shift breaks down. That's what you're saying. Because the Doppler shift is not constant, namely the actual operation is scaling. It's not Doppler shift.
Yes,
Am I right, Abel?
I think when we are dealing with the Doppler scale, we cannot compensate the inter-channel, inter-carrier interference, which giving rise to inter-symbol interference.
That's not true. Because in Zak-OTFS, so every channel, so that's exactly the point that I wanted to make. Every channel, no matter whether it's a scaling channel, accelerating channel, I don't care where the channel comes from. I don't care what is the physical mechanism behind the channel. It can be scaling, like what actually happened in reality. Every channel can be described by means of a delayed Doppler impulse response. Any channel, that's a mathematical statement. Any channel can be described as a delayed Doppler impulse response. When the channel consists of reflectors, then the delayed Doppler impulse response has physical meaning. The taps are actually the reflectors. When the channel is acceleration or scaling, the delayed Doppler impulse response don't have interpretation of reflectors anymore. It's just a function on delayed Doppler. But it's a mathematical statement that any operator, any channel, any time-varying channel can be expressed as a function on delayed Doppler. Now, and as long as this function, the effective support of this function is smaller than the period, the crystallization phenomena of Zak-OTFS will maintain. So even if you are now operating in a situation where you have a scaling channel for whatever physical reason, and the scaling will create a delayed Doppler impulse response, and you choose the periods large enough, if possible, again, that's the question. But if you choose the periods to be large enough, so the function, the delayed Doppler function which describes the channel is within the period, you will have all the phenomena that Rob described will maintain. So I don't care whether it is scaling or not. That's the point that I wanted to make.
Thank you for your answer. But just I would like to add this. Recently, I have evaluated the performance of OTFS in underwater acoustic channel. As you know, underwater acoustic channel in most of the cases is wideband or ultra wideband channel. When we compare the performance of OTFS with ODSS, namely orthogonal delay scale space modulation, which has been recently proposed by Professor I can't remember his name, sorry. In 2021, the performance of ODSS is much more better than OTFS in wideband channels.
Did you use Zak-OTFS, MC-OTFS?
I just use Zak-OTFS, yeah.
You use Zak-OTFS?
Yeah.
Okay, I need to see the paper. Perhaps,
Zak-OTFS,
perhaps if you create a modulation which is adapted to scaling, you will get a better performance. But I need to see the paper. I would like to see the comparison and then we can discuss it.
Okay, I will let you know my investigation in this regard. Thank you so much.
Very good. Communicate the results. It's interesting.
Thank you so much for your answer.
Yes. Thank you, Abed, and thank you for the answers. And we also have Professor Laius Hanzo here, and he will also like to make a question. Please say out your questions, Laius. Thank you.
Well, first of all, thank you so much, Robert, for this wonderfully entertaining exposure on this hot research subject. Much enjoyed it, and several of my colleagues were also online, so we look forward to viewing it again. And you inspired, of course, lots of questions. That was the whole purpose of this lecture. And yeah, I guess you can see from the discussions here as well that people are raising various issues. And I didn't really want to speak here, but I was kindly invited to unmute. So I just read out my question. Whether anybody has actually any thoughts concerning the potential of non-coherent detection of differentially encoded OTFS, because we have this problem with the pilot overhead. And just a quick related, well, actually unrelated comment is the Gaussian pulse idea is really brilliant, and I look forward to reading that paper. So if anybody has any comments on the non-coherent idea, that might be interesting for everybody in the group.
Of course.
I don't know. I've never thought about that particular idea, but it's an interesting question.
So you know, ultimately, sometimes people say, all right, so you gain and lose. There's no engineering solution which has only pros and no cons. And you know, one of the cons of OTFS might be really the challenge of channel estimation, or well, not necessarily just the channel estimation, but more perhaps the guard band, which you require. And you beautifully portrayed that in both the time domain as well as in the frequency domain, or delay and Doppler domain, when it comes to the aliasing problem.
Yeah, I mean, with what I was trying to do was to motivate spread pilots by saying, okay, you could use point pilots. If you use point pilots, you're going to have a guard band. And if you have a guard band, you're going to have to pay a penalty. Whereas if you use a spread pilot, you don't have to pay that penalty. Now, this question that you raise is an interesting one, because I mean, when we were just thinking about spatial diversity, right? I mean, the differential detection scheme for the Alamudi space-time block code is a particularly beautiful instance of that, right? And
indeed.
And so, I mean, I think that is an opportunity.
Yeah,
right?
absolutely, absolutely. You know, maybe just one quick point before I ring off. Really, you also alluded to the Gaussian shaping, and of course, you know, that gives us really spectral compactness in exchange for deliberately introduced controlled intersymbol interference, which then immediately requires an equalizer. And so obviously there's a trade-off there, and it is probably in your paper, but would be interesting for all of us to hear a few words on how you tackle that challenge.
So one of the Okay, so I think one of the interesting things in the paper, there's an appendix on factorizable filters. I mean, before when we were designing filters, we were doing root raised cosine, and we were doing them in dimensions. But when you think about designing a factorizable filter, there's Fourier intuition that everyone on this call has, that allows you to reason about time bandwidth expansion from the sort of the symplectic Fourier transform and what you get. But I mean, when you do factorizable filters, it's just Fourier transform stuff. But there's a very nice appendix which I recommend highly.
Can I add a word?
Well, yeah.
Lajos, if I understand your question, you're saying when you introduce a Gaussian, the Gaussian breaks orthogonality.
Yeah, definitely.
Breaks orthogonality, and you are declaring this as a price to pay. Now, this is of course true in traditional modulations which try to maintain orthogonality, like OFDM. OFDM, orthogonality is the whole point of OFDM, so anything which breaks orthogonality, like eliminating the CP or introducing a filter which it's a bad thing because it contradicts the whole paradigm. Now, in OTFS, although it is called orthogonal time frequency space, it's the opposite. It's not an orthogonal modulation. OTFS, because the data is modulated over such a fine grid, every tiny spread, every tiny delay or Doppler spread will break the orthogonality. So you will have to equalize it. So you should give up the idea of orthogonality from the beginning in OTFS. Namely, you always equalize, because the orthogonality is so sensitive in OTFS that practically it's not there. So just introduce a filter like Gaussian. You will not have orthogonality even for line of sight, even when the channel is trivial. So what? You will always have to equalize because, because that's the nature of this modulation. So that's the philosophy. The philosophy is just give up orthogonality in OTFS. It's not.
Yeah, music to my ears, Ronnie.
In a stable way anyhow.
Yeah, music to my ears. I mean, after all, Robert alluded to the IS-136 to CDMA transition, and that was in the GSM era, the second generation, where GSM already used partial response signaling. So even a quarter of a century ago or 3 decades ago, that was feasible. So not much of a problem. That's why I like the idea very much.
One of the things that we hope you like is this idea that everything's a filter. Right?
Yeah.
When we show this transceiver chain, there's a discrete filter, and then there's a transmit filter, and then we go to the time domain, and then there's a match filters on the other side. So, I mean, it's really, everything that you knew how to do about LTI channels, you get to do again.
That's wonderful. Thank you so much, folks. Yeah, much enjoyed it. Sharpening up the little gray cells.
Well, thank you for joining.
Thank you very much. Okay. Okay, thank you for the wonderful questions. I think we have more questions. I think there are several questions regarding this spread pilot you have mentioned, especially why we ended up with this rotated lattice. I think that's could you please also intuitively explain the idea?
So what I tried to do was to motivate it. Right?
Yes.
So, and in a sense, I motivated it by saying, in the radar world, radar engineers know how to do this, and they chirp waveforms. What does that look like in our world? And so what we did was we proposed something, and then Saif did this amazing calculation.
I see.
And we massaged it a little bit, but I mean, it works. In a sense, it works because it has to work and because it mimics what's true in the radar world.
I see.
And so that gave us, the radar world gave us the intuition for how to design the filter.
I see.
I mean, it wasn't that, you know, so we you know, we gained an awful lot from standing on the shoulders of radar giants.
I see. Okay. I think there are also another question is actually from Zhiqiang Wei. He's asking about the difference between delayed Doppler aliasing and delayed Doppler spread. I know there's one from the channel and one from the filter that we constructed. Do you have any comments on this?
So it gets in, so you get to the time domain using the inverse Zak transform.
That's right, yes.
Right. And the inverse Zak transform is mixing up the contributions from these replicas. And so the question is, how many of these do you feel?
I see. Right.
Okay. And if you only feel one, then you're in the crystalline regime. Crystallization conditions hold, and equalization is very straightforward. If you have aliasing, whether it's in delay or in Doppler, then you will be unpredictable because something happens at one point.
Yes.
You can't predict what's going to happen at a different point.
Right.
And so it's a lot easier to explain unpredictability than it is predictability.
I see. Okay.
Ronnie, did you want to add something?
Yeah.
So the question was regarding filter and actual physical spread.
Yes.
So what eventually affects the modulation is not the physical channel, but the physical channel twisted convolved with the filter. This is called the effective channel. We call it the effective channel. Now, what matters is the spread of the effective channel. So as long as the spread of the effective channel is smaller than the period, you will have crystallization. Now, the spread of the effective channel depends on the spread of the physical channel and the shape of the filter. Now, here you want to design filters which are narrow, which introduce minimal extension to the actual physical spread. That's the kind of wishful the design criterion. So, for example, the Gaussian filter is good because the Gaussian filter gives you small Doppler extension.
Okay. Yes. Thank you. Okay. I have a personal question regarding the spread person you have mentioned. We also had a paper several years ago. We also talked about the integration of communication and sensing. And what we propose to do is actually using the data signals in the delayed Doppler domain as the pilot for sensing. And so we do this fast time and the slow time derivation, which is exactly the discrete Zak transform. And then we concatenated this so-called post-compression model, that is the two-dimensional correlation with the transmitted signals discrete way in delayed Doppler domain. So I wonder, is this somehow reminds me of this spread person you have talking about? Because in my opinion, that after data multiplication, it also looks like a noise. So do you think do you have any comments on this kind of things?
So, okay, I would. All right. So in the talk, I stressed this idea that we are really interested in not channels, but input-output relations.
Yes.
But let me turn for a moment to like estimating channels. Okay. There's a lot of work. I mean, it begins with people like Bellow, but it ends up with people like Helmut Bolsky and Götz Vander, where they're estimating channels. And actually, probably the fundamental work is Tom Kailath, a long time ago. But when you look at their probe waveforms, they're all pulse trains.
Right.
Right. And so the idea that you can use pulse trains for estimation is very natural, and yes, it works very well.
I see.
Now, the thing is that we are actually, I mean, in what we try and explain in the second of the tutorial, the magazine articles, is we actually don't care about estimating channels. We want the interaction of the channel and the modulation to be very simple.
I see.
But we have thought about how you estimate channels and what kind of pilots you need. And, you know, we have some remarks in that second paper about what matters. You have a channel, right? And you lay it down as a blob in delay Doppler.
Right.
And you have a modulation with a certain grid. What matters is how many fundamental periods you touch.
Yes.
If you touch 2, then I can sense you with 2 pilots by solving a 2x2 system of equations.
Yes.
Right. Yes. And the same thing is true sort of more generally.
I see. I see the insight here.
Yeah. So that's okay. That was a long answer to a short question.
No, that's a very good
Sorry.
answer. No, it's all good. Thank you very much.
Okay.
I think
I have to go at 11, actually.
Ooh, I'm so sorry. I think we are actually pretty much finished with all the questions.
Okay.
And yeah, I think it's a wonderful talk. And thank you very much for being here with us today. And
well, I enjoyed it very much. And thank you very much for delivering such a great audience and great questions. Thank you.
Thank you for the audience and the speakers and Ronnie. Thank you very much. And as a last remark, that our video will be uploaded on YouTube. So I will send an email to everyone. You can have a look later. Yes.
Okay. Thank you so much.
Thank you very much. I'll see you guys next time. Bye-bye.
Bye-bye.